So for our last GIS lecture for a minute, we're going to talk about joins and overlays. And we've already talked about a lot of these concepts so far. We've talked about looking at attribute tables. I think we even talked about doing attribute table joins like database analysis a little bit earlier. So this is kind of taking it a little bit to the next level here, where we're going to be talking about spatial intersections and joins and that kind of thing. So one of the primary use of GIS is to combine different layers of information to create new information, right? Or derived information, synthetic information. So here's an example. We have slope, which classes, and we might get this from a digital elevation model. You guys will make some slope rasters a little bit later. We care about this, right? Engineers care about slope classes. And then rock competence. So this is a geologic layer or a soils layer, something like that. So a slope class, we could take a DEM raster, you could calculate slope for every pixel and then turn that into a polygon based on classes. So we, we could go by degrees or percent or something like that, right? And then we get a polygon layer. Same with soils. And then we could overlay this and do some analysis where we get competence and slope class together. And this could be something to do a landslide hazard analysis or just be an overlay that a county might want to have out there for areas to have special considerations for development, right? So there's multiple ways to attempt this, to do this. We could do a join, and a join is where you bring the data from the two things together. There has to be a target layer, and so if we want to keep this a competence layer as our target layer, then we can bring in slope class information. But you can see that the slope class has a different area to it, right? There's more smaller areas where we might have really high slopes. And so another option would be to do an overlay. And there's different ways to do this, but the idea is you bring in the information together and then you can kind of combine them. So we could have competence and slope class information spatially embedded together and kind of merge together, right? In which case you're changing and creating a new feature. So just a review of table joins. We talked about this in a previous lecture. A table join is where you have two shapefiles and they both have a common code or field in their attribute table. And so when we do a table join, we are bringing together, for example, states, and then a population, just a data table here, right? And this data table, this could be a CSV or an Excel file, is connected or joined by this common code. And so now we have our polygons, shapes of the state, and then we bring in this case, population information from a separate table. The target feature is the shapefile, and then here's a join table that comes to it. And you can join individual tables, you can join attribute tables from a different shapefile, but it's not going to change the target shapefile. It's just bringing in the database and connecting the two. And now we have additional information that we can plot. And we did this with the bridge exercise walkthrough. Yeah. Mm-hmm. Mm-hmm. Right. So the question is, when, if you, for example, had a different case, and we'll actually talk about that in a few slides, where you have multiple things that could join to one, then you have to set up some rules for how to manage that. Yeah. So there's a couple strategies that we can do. So we'll talk about spatial joins first, and this is a similar operation, and I think we actually we might have done spatial join in the bridge walkthrough. But the idea is, instead of using a code in a database to do the join, you're using a spatial relationship. So in this case, we could have a city feature class. So this would be a point. And we want to join nearby airport information, which would also be points. And so in this case, we would use a spatial operator, and this could be in this case, if it's 2 points, what operation might we need to use? A spatial operation would we need to use to join two data from 2 points together? Are they going to intersect each other? Are they going to overlap each other? Are they going to be near each other? How would you approach that? Yeah, so proximity would probably be the way to go because we're dealing with 2 points. Of course, we'll look at some other examples in a minute about how spatial features might work. And so for the spatial join, all we do is we have some spatial relationship between the target and the join feature classes. So these are 2 different shape files. And then we append information from the attribute table. So we're not changing anything to the shapefile itself. The spatial information doesn't change. We're just doing like we would the join, or bringing attribute table information. So that's what it shows right here is you're connecting the 2 tables based on a spatial relationship. And for this city and airport one, if we have 2 point feature classes, then maybe we'll just do a proximity one. Which one is the closest, right? Give me the information from the closest airport. Now, there's other options for spatial joins. We can do intersect, right? And this is where we might have 2 polygons. In this case, we have house parcel information. So here's the parcel, tax parcel, right? Your property boundary table. And it's got a lot of really specific information. It'll have the address. It'll have the home value, square footage of the buildings, number of buildings, et cetera. And then we could have zoning information, or you could have floodplain information, right? And so here's another polygon, and then the parcels will sit within the zones. So the target table is the parcel, and then the zoning information, what kind of residential or commercial is the zoning, what's the tax rate, setbacks, et cetera. This might be something a developer wants to know. Then you would join the tables that way. And this could be an intersect or is contained within that kind of thing, right? So here's that specific example of joining using proximity. We've got our cities. So the cities are the little dots right here. And then we have our airports. And we're going to create a spatial join where the 2 attribute tables are connected. So here's our city attribute table, and here's our airport attribute table. And then we're looking at proximity. Which one is the closest? So by doing that, you can add a new column, which would be distance. So what's the distance between the city and the airport? And that is a tool that I believe is in the spatial join geoprocessing tool. And so not only do you get to join that by proximity, but you then calculate the distance. These are some funny units here. Maybe that's feet. But regardless, you can do the conversion to miles or whatever that is. Granted, that's probably not going to be via a highway. That's just going to be as the crow flies, but it's still something. And then they created a new plot where they showed that you get that kind of a bigger circle depending on how far you are from an airport, right? So this is a new kind of map that tells us visually how far it is to get to an airport. So just some other examples of spatial joins. Here's an example where we have septic tanks or septic systems that have been registered with the county or the state. And then we have a geologic unit. So what kind of underlying geology do we have? And why might we care about geology for septic systems? Infiltration, yeah, so the superficial geology or soils, we could have a soil map that might have drainage capability of the soils. And are we going to have a decent drainage for the septic system and you want the water to come out and drain? Could we also expect contamination for an aquifer? Say we have nearby groundwater aquifers that are drinking water source, and we could see which septic systems might be connected in the same geologic unit, right? Is this a unit that's prone to fractures that could, transport that nastiness far away? So the septic systems are points, and that's this code right here, and then their table, and then we have the geologic units. And this is pretty obvious, right? We're just going to say it's contained within, which one contains or intersects the other. And then we bring in the geologic unit to the septic system information. So in this example, the intersect and within operators would give you the same results, but they would only differ if a particular point landed on a boundary. So right on an edge. And this can be important, especially where we have, you can see this geologic unit data. It's not going to be really precise, right? We don't have really precise maps of this. People are kind of drawing this based on topography and aerial imagery and a really small set of samples. So the within operator would yield a null result, meaning you wouldn't get a match if you selected that. The intersect operator would have 2 matches. So that's just something to check if a thing landed on a particular boundary. All right, so here's Edgar's question about cardinality in spatial joins. What if you have one state, right, but then many, in this case, counties? How do you deal with that one-to-many type of join? We need to be able to kind of anticipate that and make a plan for it so that we can get the appropriate results that we want. If we were to do this without setting anything up ahead of time, you would probably by default just get the first match information, and then you would ignore all these other things. That might be okay, that might not, depending on what you're trying to do. So how to manage what's called cardinality? We could do a number of things. So if we want to make sure that we have a kind of a row, right, for each of our potential joins, then we could set up multiple copies of the target feature until there's enough to match for each record. That's a little bit of a pain, but you could also create rules, are called merge rules, that then can bring together the multiple records that could match. So here's some examples of that. The multiple copies option is called the one-to-many join type, because a target feature can have many output copies. And so you're just basically creating enough rows to match. And then you end up with what's called a one-to-one join type, because then you have enough rows or elements to allow for each match that you could have. Just note that this join type is not the same as a cardinality type. And if this, going back to the parcel and zone example, many parcels lie within a single zone. So we could expect a cardinality of many to 1. Usually you're going to be doing, adding the zone data to the parcel data, right? So there's just one zone per parcel. But if you were to go the other way, then you'd have to set up some kind of merge rule to evaluate the number of parcels in a particular zone. In the city example, we only found the closest airport, right? And so it was just a one-to-one cardinality based on the proximity. In this case, if we had 2 airports that were exactly the same distance, then you would have a problem. You would get this null output and you would get some kind of alert. In the septic system, you might get some rare exceptions, right, where it lies right on the boundary. So you probably don't need any merge rules for this particular example. Let's look at a different example now. So we have a highway system and then a soils map, soil types. This could be really important out here on the western slope where we have shrinking and swelling soils, right? Have you guys experienced that on any of the highways out here? Yeah, the roller coaster ride, right? So kind of near Rifle on I-70 and then US 50 down to Delta. It's a big problem out here. So we could identify, I mean, at this point, we kind of know where they are, right? But you could imagine, okay, let's look on the whole western slope or some CDOT region. of where we have certain soil types that we are worried about. So you could have one highway line cross multiple types of soil, right? So how do we deal with that? If we use the join kind of technique, the spatial join technique, we could get many soils for a particular stretch of highway, but we want to keep that information in. So we need to create what's called a merge rule to deal with that and assign all the soil types to a particular line. And the way we're thinking about this is if I were to have this shapefile pulled up in ArcGIS and I clicked on it and selected it, it would show me the whole stretch that is one element within the feature class, right? One line segment. And what we're talking about right now is attaching information to that whole line segment. We're not breaking it up right now. We'll talk about breaking it up in a minute. That would be maybe another approach to take here. So when we select one element, it has one row in the attribute table. And so that's what we're dealing with. But if you were to split it, if you were to edit it and split it, or do one of the other tools that we'll talk about in a minute, you'll create many rows. We'll kind of split that line up, and then each segment will have its own row in the attribute table. So here's a merge rule for a one-to-one join. And what it's doing is setting up a way so that you can concatenate a concatenate rule. Maybe you've used that tool in Excel, where you're just adding up all the different soil types that this highway crosses. So this is my highway stretch right here, and it crosses this one, and this one. Then the join rule that you set up will just append each one it joins, right? And then it gives you a join count, how many different soil types joined. And that was important. We did this with the bridge example, where we said, okay, here's the county, that's my target feature. Here's the bridge information. And it took the first bridge that it found to be inside the county boundary and gave that information. So that's this random information for a particular soil group. But then it also counted up how many bridges that we had identified that were in poor condition fell within that county, and then ultimately use that join count to then identify counties that had a lot of bridges that were in disrepair or old. There's other options we can do too. So if you have numeric fields, you can take an average or some other statistical analysis, or you could do a sum. So for example, percent clay right here, right? You could do the average percent clay for all the different things that it intersects. It's going to be a coarse thing, right? Because you're not weighting it by the length, but it's just something else you can do. All right, so that is our join. Join has its limitations, or spatial join has its limitations, because we're not breaking up elements within a feature class. We are kind of keeping them whole. And sometimes that's good to do, and we want to do that, but sometimes maybe we want to slice and dice it a little bit more. So that's where we get into these overlays. And so overlays are when you bring things together and create a new output, like we set up initially. So an overlay of slope and rock competence yields a new feature class with fields from both that we might be able to use to assess landslide hazards. So the polygons are all split up, and it's kind of like, say you had a puzzle, right, with all the pieces together, and then you took a cookie cutter that had, maybe a cross end or something like that, and put it down on the puzzle, and you get new puzzle shapes that overlay, that combine the lines of the puzzle and the cookie cutter. And the advantage of this is that now you don't have to deal with those kind of merging rules, right? The cardinality, the one-to-one or one-to-many. You cut everything up so that each one gets its own row in the attribute table. All right, so here's a new pink polygon. You can see down here that they selected based on this. And that pink polygon fits, so it's this competence polygon within the slope class. And it's a unique combination of these two parent polygons. So it's going to have the see geology information, and then there should be a slope class in here, but I don't see that. Oh, here's the slope class. So I don't know what this number means, but that's some, oh, here it is. So slope class 1. So they gave it a categorization of slope. So this is the siltstone, right, unit that has a slope class of 1. You can see that there's going to be some higher slope classes within this unit potentially. And they're calling parents and child, right? So here are the two parents, and then they made a child. It's beautiful. By splitting the features now, you avoid that one-to-many relationship that Edgar was talking about, that plague spatial joins. So here's just some cartoons that show that. We have two different main tools for overlays. The first is intersect. And intersect just says take one feature class and then another and give me everything that intersects, but nothing else. Join it all together, line it up, do that cookie cutter combination, but I don't want anything else. I don't want any extraneous information outside of where they don't intersect, right? So that's what you end up with. And then union just brings everything together and it keeps everything. It keeps all the information. So you might not have some overlap, for example, in these outer edges outside of the circle. So there might be some cases where you want to keep that additional information, but you won't be able to do the intersected or overlay information. And you'll just have blank rows for the fields that are contained in this smaller shapefile within this feature. So some examples of unions. Here we have, let's see here. Okay, so we have geologic hazards and let's see, slope. Okay, landslide hazards. Okay, so this is the same combination that we talked about before, where we bring in the slope class and the geology. And then this is a road network. It looks like that they've overlain. So just kind of know that's a road network. But here's the underlying overlay that they created by doing an intersection between the two slope and geologic classes. And so what they ended up doing is creating a new kind of queried, they ran a query, right? And they identified sinks. So sinks are where you could have basically sinkholes, right? Or caves or kind of things caving in. So that's where we have limestone and shallow slopes. So they did a query and said, give me everything that is limestone, rock type, and low slope class. Rockfall hazards have high slopes and high geologic competence, and landslides have low competence and high slopes. Does that make sense? It's a real basic hazard analysis, but you could kind of see how we have, okay, steep, low competence, meaning it's like, you know, shale or unconsolidated stuff, soils, that kind of thing. We expect that to be able to slump and do a landslide. Rockfall hazard, well, that's going to be kind of more granite and more crystalline type rock, but high slopes. So now we get a new map that just has those categories. It doesn't cover everything because then you have some things that don't match that, right? Okay, another example is we use intersect to do a suitability analysis. And these are some examples I think you all do in this chapter 10. So they did an intersect and then they ran a query on it. And ultimately, these were used to identify snail habitat. So we had a suitable elevation range. So that was a polygon right here. So somewhere above this and somewhere below this. We had limestone, which is where the kind of soils are for this particular snail. And then we had where we had dense conifer land cover. And so all those were brought together to identify where snails can exist. So we brought in 3 together, right, in this case. So there's some limitations to what we can do when we do intersections. And we need polygon units. right? A line and polygon intersection. Okay. Oh, sorry. Intersections can be applied to all geometry types, but unions can only be performed between two polygon units. So let's just go back and look at union and intersection. So union is bringing everything together. And intersection is just showing you what overlaps. Okay, so here's a line intersecting with geology unit, and that can inform stream type. So now we get this line that has geologic information. A point over a polygon can assign polygon information to the points. But in this case, maybe a spatial join would work. I like spatial joins for points better. A cartoon of just some examples of what outputs you get. So if you intersect two polygon layers, so this one intersecting this one, you end up with this. Here's if you intersect a line. So if this is our line and we intersect it with a polygon, this is what you get. And if we intersect points with a polygon, you just get points, right? Because a point is the only place over the polygon where they match. You can intersect lines or points on a line. And so two lines intersecting gives you just the intersection of the line. A point over a line just gives you the points. And then we can intersect polygons over polygons, lines over polygons, and then points over polygons. So just a comparison, we've been talking about combining things, right, with the intersect and union tools. We do also have clip and erase, but just know that when we do these tools, clipping and erasing, we're not bringing information together, right? So these bring information from the attribute tables together. These features just do a spatial clip or erase. They're not bringing attribute table together, information together. So that's the difference between extraction tools like clip and erase and overlay tools like intersect and union. Data quality can be important, and there might be areas where we have little slivers because someone was sloppy in their delineation or the data is just kind of low resolution. And so we might need to set up tolerances so that we make sure that our data, we're getting the types of overlays and combining attribute table information that we want. So if this is a boundary that's supposed to line up with these, but it doesn't really well, then we can set up a tolerance so that our outputs work okay. But you might end up with some issues and some slivers, right? Where this should be on this side, but this little sliver ends up being a new shapefile. So you might have to go in and do some cleanup, merging slivers where you want them to merge, etc. Okay, so the last little bit here is setting up spatial joins. When we do that, let's think about some questions. What should the final output layer or table look like? Which one is our target layer? Which is the one that we want to keep and bring information into? And which one is the source layer that we're getting information from? Which spatial operator is appropriate? So do we want to do intersects? Do we want to do within, proximity? And you might try a couple different ones if you're not quite sure to see what the outputs are. You don't have to bring all the fields together. So when you do these spatial joins, you can choose which fields you want to bring over. When we did that bridge inventory example, we had dozens of fields from the bridge database. And maybe we didn't want all those. You can be selective in what you bring over. And then think about your target feature. Are you going to have multiple joins? Do you want to set up some rules to handle that, to bring in that information? So here's an example of this. A congressional staffer must provide a list of representatives from districts with at least 10 deaths from earthquakes, or we're looking into earthquake hazards. All right, they have a feature class of districts, so that's these polygons, and then earthquakes with death and damage information. All right, the desired output table is a list of districts with the congressional representatives' names and the total number of deaths in that district. Okay, so we're going to use the district shapefile as our target feature right here, congressional districts, for the 114th Congress, right? Because congressional districts change every 10 years. Then we get the earthquake information, so that's the join feature, the points. We get a new feature class. So when you do spatial joins, you're creating a new shapefile. So just keep that in mind. We're going to have a one-to-one join. I think, let's see how that goes. And then we're just going to check the information from the connection table, the earthquake table that we want to keep. And then the other thing is we're going to do a merge rule. We're going to sum, right? So we're going to sum, and then which thing do we want to sum from the join table? The number of deaths, right? So we have many points, many earthquakes in a congressional district, and we're going to sum up the deaths per earthquake. So here's what the result is. We've got the congressional district. We only kept this information, the name of the representative, the state, the district code, and then the party. And then we summed up the deaths. You can see that there's some congressional districts that didn't have any earthquakes, so we just get a null for that, and that's fine. All right. So going to the chapter 10 project, it's a map project that's already been created in the data for the textbook, and it's called Overlay Analysis Austin. So I have that open right here. This is the city of Austin boundary. And what we have, here's a lot of information. We have, let's see, we have groundwater wells. So Austin has a karst topography or geology, and karst just refers to a limestone that has a lot of holes in it. So they have sinkholes and these aquifers, and you know, there's a lot of like underground caves basically that bring water and connect it across the particular aquifer. So here's the city limit. We also have a geology layer, so that's the colors, and then the wells are the red dots. So I'm just going to run through a quick join exercise here, where we have we're going to target the geology. We're going to target the wells and bring in geology information and create a new feature class. So I'm going to go to my geoprocessing tool here, and I'm going to do spatial join. So the target feature will be wells, the join feature will be geology. And then we're going to call it, notice that it automatically goes to that geodatabase for this project. We'll call it wells geology. We're going to do a one-to-one join. So each well is going to get the information from the geology polygon. We could also do the reverse, right? So if we made geology the target feature and we did wells, we're bringing in the well information. How do we treat that? Yeah. So say I did, so in this case, the target feature is the well. So each well is going to get information from the overall geology. But if I did geology, so then wells, I'm going to have join one to many, and then I would end up with a bunch of geology layers for each well layer. That'd be kind of weird. If I kept it one-to-one, then I could do some extra stuff, and I could do, I could set up a merge rule. So I'm just going to expand this a little bit. So the merge rule, we could say, give me the, in this case, I don't really care which well information it brings over, but I could say, give me the maximum, let's see here. I'm going to do a merge rule for wells. Give me the the deepest well, right? That could be the one that I could do. Well depth, add selected, and I could get rid of that one. Let's see what other merge rules we have. You'll end up getting a join count regardless, so that's going to be nice. So that's something you could play around with if you wanted to, but we'll keep the easy one and just say, okay, wells is our target feature, geology is our join feature. They set up a merge rule, so they said, give me the first let's see, state well number. And then there's a match option right here. So we want to make sure it's within. So each well needs to be within the geologic boundary. And then I get a, let's go ahead and run it. All right, so let's open up. It looks the same, right? It's not going to change anything, but let's look at the attribute table. And so now we get, here's the well information, and then we zoom over, and then we get the geologic information right here. That was a small table that we joined. Another way to think about it, we could say, okay, give me the road network right here. I'll take the geology off. And give me the well, the distance of each well to a road, right? We could be thinking about runoff or something like that. In which case you could do the join between the wells and the road network. And we're not going to do within, but we might be, say, closest, right? You could set up a search radius, but you don't have to because it'll look as far as it needs to. Give the distance field name, so we'll just say distance. And I'm going to run this, and we'll see what it gives us, because the distance is going to be based on the projection of the file. So let's look at this one, attribute table. And here's our distance. So we don't know what these units are, but we need to check the coordinate system. What's that? Yeah, so you could do that ahead of time, and I should have done that. So if I go to wells right here, properties, and I go to source, then I go to spatial reference, and it says the unit is US survey feet. So it's a state plane. Okay. And then the streets, this is where you want to make sure everything's in the same coordinate system, right? Spatial reference, state plane, US survey feet. So if I were to do a distance between something that's in WGS 84 and state plane, I don't really know what that is. I don't know. ARC will figure something out, but it might not be super accurate. So if you're going to do something like this and you want distance and you care about it, make sure they're in the same coordinate system, so you can be sure that, okay, this is feet. In which case, when you set that field name up, you could just go distance underscore feet, and then you check that ahead of time. Next time you look at that, you're like, oh, what are the units? Oh, okay, it's feet. Great. All right, that's all I'll talk about today. Let's take some time to work on stuff.